Today we're going to complete the Ouroboros. We're going to finish our journey from the largest to the smallest, tie it all back together. On next week you have your last exam, and then Thanksgiving, of course, and then the one lecture that we have when we come back we'll use to gain perspective on everything and going forward and get ready for the final exam. So, but in a sense, this is sort of the last piece to the puzzle of the course, to the story that I've been trying to tell from the beginning. And it's an interesting way to end because we're finally getting to perhaps the smallest possible level of reality that we can reduce our understanding to, that if we can understand the universe at this level, it will give us the answers that we've been looking for everything, life, the universe, and everything, right? I mean, that title of that book, if you know what I'm talking about, is kind of a joke because those are the universal level questions that we want to understand. And this journey that we've made to try to get here, again, started a long time ago. Really started with the very first scientists trying to find an explanation for our place, how the Earth fits within the solar system within the galaxy within the universe, and ourselves in the belly of the Ouroboros. Why are we in the middle? And we're at the height of complexity. If we want to understand ourselves, we have to look at simpler and simpler levels to try to then rebuild our understanding. It's an interesting Nova last night I happened to catch. I didn't realize it was on, but it was about the mission that sent or landed a craft on a comet. And it was interesting to me, for one thing, it was just astounding in the technology and the engineering and what they were able to do. I mean, you've got a comet that's traveling, 100,000 miles an hour or 500,000 miles, really fast. And you've got to try to send a little probe out there 500 billion miles away and tell it how to land on this rough surface of a comet. And they did it. It was a really astounding achievement. But what they're looking for are amino acids. And so far they've found one, and they may find some more. And amino acids, if you recall, are the components that make up our bodies. They're the pieces of proteins that are pieced together in specific sequences by your DNA in order to construct your cells and to run all the processes in your body. So finding amino acids in comets is an interesting discovery. It was predicted by spectral analysis of comets and by some other thinking, the nebular hypothesis. Basically, when we think about the beginnings of life on the planet being seeded by comets and the amino acids that they bring. So it's interesting to be able to, really get to one and test it and find the amino acids. Yes?
Animals have amino acids?
Yes, every living being is made of amino acids. Even viruses, essentially, any protein, anything that's protein is a series of amino acids. And so yes, every cell is basically composed of amino acids. The proteins are amino acids, and then there are some other components, but the primary functional molecules of the body are made with amino acids. So it's an interesting discovery. Now, we might consider, the amino acid, the protein, the gene, the cell, sort of the basis of life. We can reduce things down to cells, understand how things work at the cellular level, and then rebuild that up into our understanding of medicine and so forth. But if we want to understand the universe, we have to get smaller than that. And as you've seen, we've gone through the process of getting into the quantum world. We've seen some very strange behaviors there, but nevertheless true. But we still want to understand what is it about the underlying nature of those particles that makes them behave differently. Why is a photon different from an electron? Why are neutrinos different? Why do the Higgs boson why do they have the properties that they have? And the explanation for that's been proposed is string theory. Now, actually, this lecture may not be, or I don't intend to be just about string theory, but that's the primary one right now, and I think it's interesting to talk about. String theory, let me just get to it, because I've already sort of set up the stage here about how we've gotten here. So let me get to, this is a little bit more of the stage. Let me do walk through a little bit though about getting back to where we started, right? Because this is getting us back to where we started. We're talking about the Big Bang. The first microseconds of the Big Bang, when everything was in a unified state. Everything was within a very hot, dense singularity that then expanded and cooled. And as it cooled, the forces separated, and then particles formed. The particles come together to form hydrogen and helium, eventually stars that explode, the hearts of those early stars creating the heavier elements, which are then spread throughout the universe and recollapse into a second generation of stars, including our own planets around those stars and so forth. So we've walked through that large-scale thing. We talked about at the very beginning how those first microseconds, we understand down to about 3 seconds pretty well what happened. But within those first few billionths of a second, we still don't quite know exactly what the nature of that singularity was. But we might find that out at the Large Hadron Super Collider, and it may lead us to this theory, to a unified theory, where all the forces are unified in one understanding. Keep in mind, we've been unifying things all along. We're trying to get the last piece. And we had electricity and magnetism and light, completely separate forces, until we realized the electromagnetic force carried by photons actually interacts with the electrons and generates all three of those forces. So we've unified that. We haven't unified those forces with the strong and weak nuclear forces and with gravity. We've unified thermal properties with those things. So there's been a lot of unification going on over the years. We just want to take the final step. And this really is an ongoing process. I want you to, what I really want you to appreciate is just how much is happening right now. You know, when we show some of these things, this is one of the areas where I'm trying to keep up with what's going on more than almost any other area, because inflation theory, which replaced the Big Bang theory, was in the 80s. So about the time I was an undergrad, and I wasn't studying physics at the time, they completely revolutionized our understanding of the Big Bang. Since then, we've gone through 2 or 3 other revolutions in our understanding. The supersymmetry idea of the Standard Model, the emergence of the Standard Model itself. These things have revolutionized our understanding of physics just in the last few decades. Just in the last decade or so, string theory has given us something, actual testable hypotheses that may be able to be tested at the Hadron Super Collider and give us a unified theory of everything. So I'm going to let Brian Greene tell you more about it. He'll tell you basically what string theory is and what its promises are. A lot of Brians in physics for some reason. Brian Cox and now Brian Greene, like a Monty Python skit. But maybe there's a connection there between physics and Monty Python. There may be. But I'll let Brian Greene, again, say more, and then I'll come back. I'll just play the video. Come on.
In the year 1919, a virtually unknown German mathematician named Theodor Kaluza suggested a very bold and, in some ways, very bizarre idea. He proposed that our universe might actually have more than the 3 dimensions that we are all aware of. That is, in addition to left, right, back, forth, and up, down, Kaluza proposed that there might be additional dimensions of space that for some reason we don't yet see. Now, when someone makes a bold and bizarre idea, sometimes that's all it is. Bold, bizarre, but has nothing to do with the world around us. This particular idea, however, although we don't yet know whether it's right or wrong, and at the end I'll discuss experiments which in the next few years may tell us whether it's right or wrong, this idea has had a major impact on physics in the last century and continues to inform a lot of cutting-edge research, so I'd like to tell you something about the story of these extra dimensions. So where do we go? To begin, we need a little bit of backstory. Go to 1907. This is a year when Einstein is basking in the glow of having discovered the special theory of relativity and decides to take on a new project to try to understand fully the grand pervasive force of gravity. And in that moment, there were many people around who thought that that project had already been resolved. Newton had given the world a theory of gravity in the late 1600s that works well, describes the motion of planets, the motion of the moon, and so forth, the motion of powerful apples falling from trees, hitting people in the head. All of that could be described using Newton's work, but Einstein realized that Newton had left something out of the story because even Newton had written that although he understood how to calculate the effect of gravity, he had been unable to figure out how it really works. How is it that the sun, 93 million miles away, somehow it affects the motion of the Earth? How does the sun reach out across empty, inert space and exert influence? And that is the task to which Einstein set himself, to figure out how gravity works. And let me show you what it is that he found. So Einstein found that the medium that transmits gravity is space itself. The idea goes like this. Imagine space as a substrate of all there is. Einstein said space is nice and flat if there's no matter present. But if there is matter in the environment, such as the sun, it causes the fabric of space to warp, to curve, and that communicates the force of gravity. Even the Earth warps space around it. Now look at the moon. The moon is kept in orbit, according to these ideas, because it rolls along a valley in the curved environment that the sun and the moon and the Earth can all create by virtue of their presence. We go to a full-frame view of this. The Earth itself is kept in orbit because it rolls along a valley in the environment that's curved because of the sun's presence. That is this new idea about how gravity actually works. Now, this idea was tested in 1919 through astronomical observations. It really works. It describes the data. And this gained Einstein prominence around the world. And that is what got Kaluza thinking. He, like Einstein, was in search of what we call a unified theory. That's one theory that might be able to describe all of nature's forces from one set of ideas, one set of principles, one master equation, if you will. So Kaluza said to himself, Einstein has been able to describe gravity in terms of warps and curves in space, in fact space and time to be more precise. Maybe I can play the same game with the other known force, which was at that time known as the electromagnetic force. We know of others today, but at that time that was the only other one people were thinking about. You know, the force responsible for electricity and magnetic attraction and so forth. So Kaluza says, maybe I can play the same game and describe electromagnetic force in terms of warps and curves. That raised a question. Warps and curves in what? Einstein had already used up space and time, warps and curves, to describe gravity. There didn't seem to be anything else to warp or curve. So Kaluza said, well, maybe there are more dimensions of space. He said, if I want to describe one more force, maybe I need one more dimension. So he imagined that the world had 4 dimensions of space, not 3. And imagine that electromagnetism was warps and curves in that 4th dimension. Now here's the thing, when he wrote down the equations describing warps and curves in the universe with 4 space dimensions, not 3, he found the old equations that Einstein had already derived in 3 dimensions, those are for gravity, but he found one more equation because of the one more dimension, and when he looked at that equation, it was none other than the equation that scientists had long known to describe the electromagnetic force. Amazing. It just popped out. He was so excited by this realization that he ran around his house screaming victory, that he had found the unified theory. Now clearly, Kaluza was a man who took theory very seriously. In fact, there's a story that when he wanted to learn how to swim, he read a book, a treatise on swimming, then dove into the ocean. This is a man who would risk his life on theory. Now, but for those of us who are a little more practically minded, two questions immediately arise from his observation. Number one, if there are more dimensions in space, where are they? We don't seem to see them. And number two, does this theory really work in detail when you try to apply it to the world around us? Now, the first question was answered in 1926 by a fellow named Oscar Klein. He suggested that dimensions might come in two varieties. There might be big, easy-to-see dimensions, but there might also be tiny, curled-up dimensions, curled up so small, even though they're all around us, that we don't see them. Let me show you that one visually. So imagine you're looking at something like a cable supporting a traffic light. It's in Manhattan, New Central Park, and it's kind of irrelevant. But the cable looks one-dimensional from a distant viewpoint. But you and I all know that it does have some thickness. It's very hard to see it, though, from far away. But if we zoom in and take the perspective of, say, a little ant walking around, little ants are so small that they can access all of the dimensions. The long dimension, but also this clockwise, counterclockwise direction. And I hope you appreciate this. It took so long to get these ants to do this. But this illustrates the fact that dimensions can be of two sorts, big and small, and the idea is that maybe the big dimensions around us are the ones that we can easily see, but there might be additional dimensions curled up sort of like a circular part of that cable, so small that they have so far remained invisible. Let me show you what that would look like. So if we take a look, say, at space itself, I can only show, of course, two dimensions on the screen. Some of you guys will fix that one day. But anything that's not flat in the screen is a new dimension. Goes smaller, 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 and way down in the microscopic depths of space itself. This is the idea. You could have additional curled up dimensions. Here is a little shape of the circle, so small that we don't see them. But if you were a little ultra microscopic ant walking around, you could walk into big dimensions that we all know about. That's like the grid part. But you could also access a tiny curled up dimension that's so small that we can't see with the naked eye or even with any of our most refined equipment, but deeply tucked into the fabric of space itself, the idea is there could be more dimensions, as we see there. Now, that's an explanation about how the universe could have more dimensions than the ones that we see, but what about the second question that I asked? Does the theory actually work when you try to apply it to the real world? Well, it turns out that Einstein and Kaluza and many others worked on trying to refine this framework and apply it to the physics of the universe as was understood at the time, and in detail it didn't work. In detail, for instance, they couldn't get the mass of the electron to work out correctly in this theory. So many people worked on it, but by the 40s, certainly by the 50s, this strange but very compelling idea of how to unify the laws of physics had gone away. Until something wonderful happened in our age. In our era, a new approach to unify the laws of physics is being pursued by physicists such as myself and many others around the world. It's called superstring theory, as you were indicating. And the wonderful thing is that superstring theory has nothing to do at first sight with this idea of extra dimensions. But when we study superstring theory, we find that it resurrects the idea in a sparkling new form. So let me just tell you how that goes. Superstring theory, what is it? Well, it's a theory that tries to answer the question, what are the basic, fundamental, indivisible, uncuttable constituents making up everything in the world around us? The idea is like this. So imagine we look at a familiar object, just a candle and a holder, and imagine that we want to figure out what it is made of. So we go on a journey deep inside the object and examine the constituents. So deep inside, we all know you go sufficiently far down, you have atoms. We also all know that atoms are not the end of the story. They have little electrons that swarm around the central nucleus with neutrons and protons. Even the neutrons and protons have smaller particles inside of them, known as quarks. That is where conventional ideas stop. Here's the new idea of string theory. Deep inside any of these particles, there is something else. The something else is this dancing filament of energy. It looks like a vibrating string. That's where the idea of string theory comes from. And just like the vibrating strings that you just saw in a cello can vibrate in different patterns, these can also vibrate in different patterns. They don't produce different musical notes, rather they produce the different particles making up the world around us. So these ideas are correct. This is what the ultra-microscopic landscape of the universe looks like. It's built up of a huge number of these little tiny filaments of vibrating energy, vibrating in different frequencies. The different frequencies produce the different particles. The different particles are responsible for all the richness in the world around us. And there you see unification, because matter particles, electrons and quarks, radiation particles, photons, gravitons, are all built up from one entity. So matter and the forces of nature all are put together under the rubric of vibrating strings, and that's what we mean by a unified theory. And here is the catch. When you study the mathematics of string theory, you find that it doesn't work in a universe that just has 3 dimensions of space. It doesn't work in a universe with 4 dimensions of space, nor 5 nor 6. Finally, you can study the equations and show that it works only in a universe that has 10 dimensions of space and 1 dimension of time. Leads us right back to this idea of Kaluza and Klein that our world, when appropriately described, has more dimensions than the ones that we see. Now you might think about that and say, well, okay, if you have extra dimensions and they're really tightly curled up, yeah, perhaps we won't see them if they're small enough, but if there's a little tiny civilization of green people walking around down there, you make them small enough and we won't see them either. That is true. One of the other predictions of string theory. No, that's not one of the other predictions of string theory. But it raises the question, are we just trying to hide away these extra dimensions, or do they tell us something about the world? And the remaining time, I'd like to tell you 2 features of them. First is, many of us believe that these extra dimensions hold the answer to what perhaps is the deepest question in theoretical physics, theoretical science. And that question is this. When we look around the world, as scientists have done for the last 100 years, there appear to be about 20 numbers that really describe our universe. These are numbers like the mass of the particles, like electrons and quarks, the strength of gravity, the strength of the electromagnetic force. A list of about 20 numbers that have been measured with incredible precision, but nobody has an explanation for why the numbers have the particular values that they do. Now, does string theory often answer? Not yet, but we believe the answer for why those numbers have the values they do may rely on the form of the extra dimensions. And the wonderful thing is, if those numbers had any other values than the known ones, the universe as we know it wouldn't exist. This is a deep question. Why are those numbers so finely tuned to allow stars to shine and planets to form when we recognize that if you fiddle with those numbers, if I had 20 dials up here and I let you come up and fiddle with those numbers, almost any fiddling makes the universe disappear. So can we explain those 20 numbers? And string theory suggests that those 20 numbers have to do with the extra dimensions. Let me show you how. So when we talk about the extra dimensions in string theory, it's not one extra dimension, as in the older ideas of Kaluza and Klein. This is what string theory says about the extra dimensions. They have a very rich, intertwined geometry. This is an example of something known as a Calabi-Yau shape. Name isn't all that important, but as you can see, the extra dimensions fold in on themselves and intertwine in a very interesting shape, interesting structure. And the idea is that if this is what the extra dimensions look like, then the microscopic landscape of our universe all around us would look like this on the tiniest of scales. When you swing your hand, you'd be moving around these extra dimensions over and over again, but they're so small that we wouldn't know it. So what is the physical implication, though, relevant to those 20 numbers? Consider this. If you look at the instrument, a French horn, notice that the vibrations of the air strings are affected by the shape of the instrument. Now in string theory, all the numbers are reflections of the way strings can vibrate. So just as those air streams are affected by the twists and turns in the instrument, strings themselves will be affected by the vibrational patterns and the geometry within which they are moving. So let me bring some strings into the story. And if you watch these little fellas vibrating around, they'll be here in a second right there, notice that the way they vibrate is affected by the geometry of the extra dimensions. So if we knew exactly what the extra dimensions look like, we don't yet, but if we did, we should be able to calculate the allowed notes, the allowed vibrational patterns. And if we could calculate the allowed vibrational patterns, we should be able to calculate those 20 numbers. And if the answer that we get from our calculations agrees with the values of those numbers that have been determined through detailed and precise experimentation, this in many ways would be the first fundamental explanation for why the structure of the universe is the way it is. Now, the second issue that I want to finish up with is, how might we test for these extra dimensions more directly? Is this just an interesting mathematical structure that might be able to explain some previously unexplained features of the world? Or can we actually test for these extra dimensions? And we think, this is, I think, very exciting, that in the next 5 years or so, we may be able to test for the existence of these extra dimensions. Here's how it goes. In CERN, Geneva, Switzerland, a machine is being built called the Large Hadron Collider. It's a machine that will send particles around a tunnel, opposite directions, near the speed of light. Every so often, those particles will be aimed at each other, so there's a head-on collision. The hope is that if the collision has enough energy, it may eject some of the debris from the collision from our dimensions, forcing it to enter into the other dimensions. How would we know it? Well, we'll measure the amount of energy after the collision, compare it to the amount of energy before, and if there's less energy after the collision than before, this will be evidence that the energy has drifted away, and if it drifts away in the right pattern that we can calculate, this will be evidence that the extra dimensions are there. Let me show you that idea visually. So imagine we have a certain kind of particle, it's called a graviton. That's the kind of debris we expect to be ejected out if the extra dimensions are real. But here's how the experiment will go. You take these particles, you slam them together, and if we are right, some of the energy of that collision will go into debris that flies off into these extra dimensions. So this is the kind of experiment that we'll be looking at in the next 5, 7 to 10 years or so, and if this experiment bears fruit, if we see that kind of particle ejected by noticing that there's less energy in our dimensions than when we began, this will show that the extra dimensions are real. And to me, this is a really remarkable story and a remarkable opportunity. Going back to Newton, with absolute space, didn't provide anything but an arena, a stage in which the events of the universe take place. Einstein comes along and says, well, space and time can warp and curve. That's what gravity is. And now, string theory comes along and says, yes, gravity, quantum mechanics, electromagnetism, all together in one package, but only if the universe has more dimensions than the ones that we see. And this is an experiment that may test for them in our lifetime. Amazing possibility. Thank you very much.
All right, so again, as before, you can sort of see that that was 2005. 10 years later, or almost 10 years later now, we're still waiting for some of that experimental evidence. But there's a lot of other ideas that have been emerging as well from this string theory. So I'll just walk through a little bit of it. One of the challenges of string theory early on was someone announced a string theory. Said, oh, I've got this great new theory. And then somebody else came out and said, oh, I do too. I've got one too. And they were different. And then it turned out there were like 9 people who said they had their own string theory. And that doesn't make sense. The universe has to have one, right? There has to be one theory if it's a unifying theory. There can't be 9 possible answers. They looked at it more closely and realized, oh, well, these calculations really are the same, and they unified them into what was more appropriately now called M theory. And M stands for M-brain, not membrane like in biology, but an M-brain. A brain is a sheet of the universe, a fabric, essentially, that contains all of these dimensions. Again, I'm going to go into all the details between P brains and M brains. They may say something about the physicists that they're calling these things P brains. Anyway, that's neither here nor there. But what this presents us is another possible multiple universe explanation. Because these brains, a single brain, can contain an entire universe. And there could be multiple brains. Matter of fact, the Big Bang might have been a collision of two brains that then generated the energy, the singularity that led to our universe. And the idea is that each possible combination of those 20 numbers that he talked about does exist in a separate universe. Now that's not an infinite number, but it's a very large number. If you take 20, factor the factorial of 20 possible numbers, the number of combinations there, it's a large number, but it's not infinite. So this isn't like the many worlds hypothesis, but the idea being most of those universes, of course, would be empty because those numbers wouldn't work. A number of them would have planets and suns and life and so forth, and ours was one of them. So it's interesting, again, sort of things to think about there, and that this process may be cyclic. Now, I don't take too much time on this either, but this question of whether or not the universe will just eventually peter out, because entropy will eventually become, spread everything out, and it'll go to sort of an inert, empty universe, or could it recollapse and be Big Bang again? Could it be cyclic? And is there enough mass in the universe to slow it down and bring it back together? Well, this was a big question for a long time, and what led to one of the discoveries that has been the most significant recently. When you look for the mass that it would take, they realized that not only is the universe not slowing down, but it's actually accelerating. It's still expanding faster and faster. It's not slowing down. It doesn't look like it's coming anywhere close to ever being able to collapse again. Not only can we not account for all of the mass that we measure through gravitational lensing and so forth and these other tools, when we look out into space and we see luminous matter, things that glow brightly like with sunlight, there's dark matter out there. There's a lot of matter that we can't see. That doesn't mean we can't understand it. It just means we can't see it with photons, by bouncing photons off of it or any other part of the electromagnetic spectrum. It doesn't interact with that force. There's also dark energy that is pushing against gravity and causing the universe to expand. Again, this is an even weaker force that only operates over very great distances. But gravity itself is an odd force because it's so much weaker than the electromagnetic force. And we've talked about that a number of times. What makes gravity so weak compared to the electromagnetic force? If it wasn't, of course, there wouldn't be any complexity. Everything would be collapsed into a black hole. Because when there is enough matter for gravity to overcome the electromagnetic force, that's what you get. So these are all some really interesting questions, and these are some of the things that are left open in these first few milliseconds, and that we might eventually get answers to through string theory. So string theory is an interesting approach. It's not the only one. There are some other ideas. Loop quantum gravity, which is another way of unifying things. But there may also be the possibility that, again, the ideas of loop quantum gravity and string theory are really very similar and will be combined into another combination. So what's exciting about this, and what I want you to understand about this theory going forward, is that we're still searching for answers. This is a very active, ongoing, exciting process and endeavor, right? Typically, you come into a college classroom and I tell you what we already know. All right, this is what we know. We've learned all this stuff, and this is what you need to know about all this stuff that we know, so that you can go out and be a literate human being, member of our society, right? So here's what you need to know, right? It's like you ask me, just tell me what I need to know on the test, right? Well, I think it's more exciting to see the frontiers where we're still asking questions, where we're still looking for answers. We do know a lot. Remember, the nature of a theory is to take everything we know and explain it. Find a way of explaining it. Why is it like this? In a way that can be tested and can then make predictions about those tests and other questions that we might have. And string theory is not technically a scientific theory yet. Theoretical physics is a little bit outside the normal practice of science in that it starts with these weird ideas, and then we still call them theories, but they're not necessarily the same unifying theories that plate tectonics or evolution or something like that serve until they become testable. So string theory is a candidate, sort of a unified theory candidate, or a candidate theory that is pretty interesting and very exciting. And if we do start getting some experimental results on some of these questions, one of the explanations of why the gravity is so weak is that it spends much of its time in these smaller dimensions and not all of its time in R3, so that we're only experiencing the force 3/10 of the time, right? Whereas the electromagnetic force is constrained within R3 dimensions, and so it's much stronger. So there's a lot of interesting things here. I want to end with another video that I promised you that's sort of funny. But I want to talk a little bit about time first, because we tend to sort of just accept time as a given. We think, oh, well, time, it's easy to understand. Time progresses, right? We can measure it, seconds, minutes, hours, years, eons, whatever unit of time you want to put together. It's conceivable. We understand time. And it only goes forward, right? Time, unlike the other dimensions, as he mentioned, you can go up or down. You can go forward or back. You can go left or right. But you can only go forward in time. Time is the only dimension that seems to only travel in one direction. Now, why is that? Why isn't time like the other dimensions? If we're describing time as a dimension, what's so unique about it that limits us into only going forward? And the answer to that is entropy. Entropy is the thermodynamic process of tendency towards disorder, and it, again, guides the organization of complex systems and all kinds of things to accelerate this overall process within the universe of entropy. And the point is, things do not tend to go backwards in terms of entropy. If you break an egg, it's not likely to go back together. Now, that's possible within the laws of physics. It's just so highly unlikely. I think one of the better examples I've seen is if you go to see a statue, right? Go see Michelangelo's David in Italy or something, and all of a sudden it's arm waves at you. We would not expect to see that, right? It's solid stone. That's not going to happen. Well, actually, we can calculate the probability of that happening. That arm is made up of trillions of molecules. Each one of those molecules is made up of quantum particles that do have this range of probabilities. If, in the extreme chance, every one of those quantum particles just happened to vibrate in the same direction simultaneously, you could actually see the arm of a solid statue wave at you. Now, that's possible, but it's so unlikely we're never going to see it, right? Even in the age of the universe, 13.7 billion years, doesn't give us enough time for that event to have had any real chance of happening. But who knows? Maybe one of these days somebody will say, oh, I saw the statue's arm wave, and it actually did. It's an interesting question because, it's sort of like I always think about as kids, right? We're told everything's possible. And then as kids we start saying, well, not everything. I can't put my egg back together. Because we can all think of all these things that really are impossible. And now we come back around full circle almost to the fact that, well, everything is possible, but most these things that we're talking about are so improbable that we're never going to see them. And again, that was some of the fun that was in Hitchhiker's Guide to the Galaxy and a lot of the literature that's been written using string theory and quantum mechanics and these probability functions in literature. It's interesting. But if time is limited by entropy, and we only see time go forward because we only see entropy tending towards disorder, if we could ever, this is another possibility, if we could ever reverse entropy, could we reverse time? And this gets us right back into those many worlds interpretations in which everything has basically already happened. We're just moving through whichever path we take throughout this this range of possible futures. Because for that to be true, for us to be able to reverse enter and reverse time, we would have to be able, we would basically be doing that. We would be traversing different paths through this infinite. Some people I've seen describe it as a loaf, almost like a loaf of bread, and you can go slice to slice to slice. Every moment of our existence, we're in this slice, and then we go to the next slice and the next slice. When we're the one moving, time, the universe, everything else is already there. We're just moving through it. It's an interesting idea. All right. Let me show you one more thing. Now, this is the same guy that I think I'm going to stop showing the first one because it's not nearly as much fun as this one. But I'm going to go and show this one. He's going to talk about string theory. It's the same grad student. This one is to Bohemian Gravity, or Bohemian Rhapsody is the song that he's using here. Oh, come on. Let's see if it'll get me there.
Really? It's not worth it.
No worries, I got this.
Is string theory right? Is it just fantasy? Caught in the landscape, out of touch with reality. Compactify on a spy or star as 3. Spaces of pure void. Why should it be stringy? 'Cause it's quantum dot, classical, non-renormalizable. Anywhere you quantize to encounter infinity. You Angels so don't shake from the string theory. Railroad by a voice in the tree. Fairy bones, open goals, oriental gold. Vibrations on, thinking of particle vertical. Vibrations, thinking of particle vertical. Vibrations, thinking of particle vertical. Thinking of particle vertical. Thinking of particle vertical. Mamma mia, mamma mia. Such a simple particle.
Tell a story. He's going to go ahead and talk a little bit longer, but I'm going to tell. All right. So I think that's really funny. And at least after what we've been talking about, some of it may have struck you as funny as well, and some of it's well beyond me to understand what he's talking about. But what's fascinating to me is that this is where we are. I mean, this is pretty current with what's going on right now in the fields of science and quantum physics and so forth. So you can see how complex it actually gets. You know, I try to simplify as much as possible to try to get an explanation for, or try to just get a description of where we are with things. He's, of course, been singing that mainly for other grad students, I assume. But there's a lot of really interesting stuff going on now. He's actually a master's student, so he's not even a PhD student. So if you go into physics, like my daughter wants to do, that's where you go. So I'm anxious. I'm anxious for my daughter she's in 8th grade now. I'm anxious for her to become a physicist so she can catch me up on stuff and tell me what's going on. All right, true or false? Strings are vibrating energy with different frequencies. True. If the theory is correct, everything is made up of these different vibrations of strings. So is the universe on a string or in the palm of your hand? This is just a joke, again, like the last one where, I don't know why there's a link on hand. These are both just like poetic descriptions of fate and whatever, right? I've got the universe on a string, or I've got the world in the palm of my hand, that kind of thing. So it's one or the other, maybe. I will say true. Again, I'm sure these are set up to be either true or false. True or false, this is a cartoon. Let me see if it'll open. This one? That's the cartoon. True or false? Is that a picture of entropy? Poor guy starts to carve it. By the time he's finished, it's already falling apart. True. Okay, that's true. And then true or false, time is a river? Another cliche, it flows. Or time is a thief. Yeah, right? I mean, it sort of feels that way sometimes. It goes so fast, it steals opportunities and so forth. So,
The first one was false.
what did I say about the first one? This was weird. This one's set up differently, so I'm not sure where it went. We might have actually just done the sort of intro quiz rather than the whatever. We've got, oh yeah, here's the string theory quiz. Hold on. So we said, do you have the universe on a string or in the palm of your hand? We said true, what I said. We'll see how it comes out. Strings are vibrating energy with different frequencies. That's true. That's the one that is actually a real question. There's our entropy cartoon. We said true. Time is a river. We said true. Time is a thief. We said true. All right. So, yeah, it's set up where pretty much most of these, anything you say is probably true. But we said true, 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 true. So, all right. All right, see those of you in lab in a little bit who are coming today. The rest of you I'll see on Tuesday for the test, for the last test.